Hello. In this video, I want to analyze the forces of a block on an inclined plane. It's something we've looked at a lot in class. So here below, we have our inclined plane, and it's inclined at angle theta, and we have a block resting on it. And the first step in doing this should be to just think, what are the forces acting on the block itself? So if I draw a little point here, you should be able to think about at least one force acting on it. The easiest one is to think of just the force of weight pulling it down, or as you guys say in class, it's the force of gravity. So I'll just represent this by F subscript W as the force of weight that's given by the mass of the block times the acceleration due to gravity. So that's acting on it. But is there another force acting on the block? Think about it for a second. If weight was the only one acting, it would just fall straight down. So something's holding it up. What's holding it up? It's the plane, the inclined plane. So the inclined plane is holding it up, but not in a force that goes directly straight up, opposing weight. The inclined plane can only exert a force that's perpendicular to it. So it goes like this. This we'll call the normal force. I'll represent that by F subscript N. Now, if this is a frictionless plane, and let's imagine that it is for the moment, then there are no other forces acting on it at all. Now, one of the things that we want to do if we have a situation like this is we're mostly concerned with the block sliding down the plane, something like this, in this direction. So there is no force that's actually pushing it down the plane. And if there's no force pushing it down the plane, then what we want to do is somehow figure out how it could be pushed down the plane. Well, can the normal force do that? Well, it can't really because it's perpendicular to the plane. One way to see that is imagine if I had a little bit of a flashlight here and I shone it right there like that. And if I shine the flashlight in this direction, no shadow of this vector, this normal force vector, would appear on the plane. It would just be a little dot. So that means there's no component of the normal force that's going down the plane. That's not really happening, okay? Now, on the other hand, if I took the same type of flashlight, if I took this flashlight and I copied it and I put it down here, pasted it, and then I rotated it around so that it's in the same sort of axis, so now it's pointing in the same direction as this guy. If I put this guy here, what would happen is this would actually cast a bit of a shadow for the weight vector, some shadow of it, right? If this light was shining down, it would cast some shadow on this plane like this. It would go in that direction. And so what I want to do is figure out how we can get this particular vector right here. So let's see if we can get that vector from the weight vector, the FW that we just looked at here. So let me erase a bunch of stuff. Let's get rid of this guy. So what I want to do is figure out how we can get that. In order to do that, what we're going to do is resolve this vector, the weight vector, into the coordinate system of the block. And so we imagine the block in a coordinate system that's going down the plane. We'll call that positive, and we'll call this the positive direction for y. So this is y and this is x. I want to have a component of the weight vector that is moving in the positive x direction. So that'll tell me how I can get this block moving down the plane. So one way of doing that is I say, okay, let's imagine this shadow that I talked about earlier. This could be a component of this weight vector that goes like this. And then I have another component of the weight vector that goes like this. And these two components are 90 degrees from each other. All right? So we have something like that. Now, if I know this angle is theta here, because of similar triangles, that angle will also be theta. And so the hypotenuse is the one here. This is the weight, that's the hypotenuse. And what I want is now these components, this dashed line here and this dashed line here. So because this side is adjacent to the angle theta, then this is going to be mg cosine theta, because cosine is adjacent over hypotenuse, and this is the adjacent side. The opposite side is over here. So this is going to be opposite of the angle, so this is going to be mg sine theta, like that. So mg sine theta is the force that's going to be pushing it down the plane, like this, as we were talking about before. That's the force we were looking for. That's the component of the weight that pushes it down the plane, mg sine theta, if it's inclined at angle theta. So now I can write some force diagrams. Using the force diagrams, I can basically write the sum of the forces in the y-axis equals the mass of the block times the acceleration that it experiences. And I can also do the sum of the forces in the x direction equals the mass of the block times the acceleration it experiences in the x and in the y. So let's take a look at the forces acting in the y direction first. So remember, here we have our y-axis. Y-axis is there, and the x-axis is this way. So let's just take a look at things in the y-axis. So in the y-axis we have this one. So that's the normal force that's going positive. And in the negative direction we have mg cosine theta. Okay? So that is going to let me write these things in the y-axis. So plus is going to be the normal force. That's the normal force going up. And in the negative direction I have mg cosine theta. Cosine theta. And that is going to equal the mass times the acceleration in the y direction. And let me shrink this guy and move it a little bit. Resize. Okay, and I'm just going to move that over there. And I'm going to continue with this, and let's just work on this equation. This is a perfectly valid equation for the forces in the y direction, but we can do better with it. So let's take a look at the y direction. What's going on in the y direction? So the normal force is pointing up, and mg cosine theta is pointing down. But is this block actually moving up or down like this? Is it accelerating in the y-axis? It's not. So actually the acceleration in the y-axis is 0. So let's rewrite this equation like this. The normal force is positive, minus mg cosine theta equals m times 0. Well, that must equal 0. So I have the normal force minus mg cosine theta equals 0. I can just add mg cosine theta on both sides. So I add that. And it cancels here. And then I get Fn equals mg cosine theta. That's my equation for the sum of the forces in the y direction. So those forces must balance out. So what we know is that this normal force here has got to be exactly equal to mg cosine theta. And there's no acceleration in the y. All right? So that's what we have in the y-axis. Let's take a look at the x-axis. And again, in the x-axis, the only force we have pulling it down is mg sine theta. And that's in the positive x direction like this. This is positive here. Okay, so I can say mg sine theta equals the mass of the block times the acceleration it will experience in the x direction. That's a perfectly valid equation. I can just box that right like that. I can simplify it a little bit further if I want. I can cancel out the m's, and so I could get something like this: g sine theta equals the acceleration in the x direction. It's another way of saying the valid equation. So these two equations are the ones that govern the motion of the block on the inclined plane. Hopefully this is the kind of thing you can stop and pause and go back and look at if there's some part that I went over too quickly. And I'm hoping that this will be a breakdown that will prepare you guys for the exam. Okay, we'll stop now.